I welcome you all to the presentation on Enclosure and Design of Conical Head. So I am Dr. G. Kirtiga, Associate Professor of Chemical Engineering. So here we will be discussing about the pressure vessel, its component, different type of heads, and also we will solve a problem on conical head. Coming to the definition of a pressure vessel is a closed container designated to hold gases or liquids at a pressure substantially higher than the ambient pressure. Some of the pressure vessel includes chemical reactors, distillation column, boilers, heat exchanger, LPG storage tanks and autoclaves. So whatever device we are using in the chemical industries, can be classified as a pressure vessel. Based on the type of pressures, the pressure vessels are classified as low pressure vessel, medium pressure vessels and high pressure vessels. High pressure vessels have pressures or withstand pressures greater than 300 psi. Some of them include a CNG reactor, ammonia synthesis reactor, FCC reactor and hydrogen storage vessels. Medium pressure vessels operate between 15 to 300 psi. Some of them are heat exchangers, evaporator, distillation column and a closed reactor. The next one is low pressure vessels, which has less than 15 psi or approximately equal to atmospheric pressure. Some of them are water tank, mixing tank and fermentation tank. Coming to the design consideration, we will briefly discuss the design factors which has to be considered during the design of a pressure vessel. Some of them are design pressure and temperature, material of construction, corrosion allowance, joint efficiency, safety factor, and applicable design code. Coming to the design pressure and temperature. So, we are including the design pressure and temperature under the design consideration as it ensures safety, reliability, and durability of the pressure vessel. So the design pressure should always be the maximum pressure of the vessel, which is higher than the operating pressure. So design pressure is a pressure which, which the vessel can withstand, and it should be higher than the operating pressure. And design temperature can be a minimum or a maximum temperature considered to design the material selection and allowable stress. So next, coming to the material of constructions, there are numerous material of construction based on the properties of the working liquid. We have to choose the material of construction. Some of them are carbon steel, alloy steel, stainless steel of 304 grade and 316 grade, nickel alloy, titanium alloy, glass lined reactor, rubber lined reactor. Say for example, dilute acids, we can go for stainless steel. And if you have strong acids, we can go for nickel or titanium alloys. Say if you have a corrosive condition like acid condition, then we can go for glass lined reactors. So the material of construction is based on the properties of the material and it adds to the cost of the design. Next, coming to corrosion allowance. So this corrosion allowance is an important factor in the design consideration. So it is the additional thickness or the intentionally added thickness to your pressure vessel to compensate for the expected material loss. Okay, so this addition of corrosion allowance increases the service life of the vessels. It prevents the leakage and rupture of the vessel under any drastic conditions. So it has been selected based on the design code and safety standard. And for mild corrosive, we always add a corrosion allowance of 2 mm. And if it is highly corrosive, we should add 4 to 6 mm. So this corrosion allowance is the thickness, extra thickness which is added to the design thickness, so that the material will be highly thick than the design of the vessel. So the whole idea is to withstand the corrosion properties of the material during the operation. Then coming to joint efficiency. This joint efficiency is represented by a factor known as capital J. It refers to the strength of the weld joint relative to the strength of the original material. So wherever in a process vessel we have a joint, so we have any welding happening, so this joint efficiency will ensure, the factor tells how safe the joint is. So if J is equal to 1, it is fully radiographed and butt welded. So after welding, we do some radiographic test and categorized it as no leak efficient from the joints. That is 1. So if one condition of 1 is used for high pressure vessels and also for certain corrosive condition where the leakage has to be prevented. Similarly, we can go for J is equal to 0.85 for spot welding kind of joints where the factor of safety is 85%. Similarly, it can be still lower for room temperature operated vessels where the leakage can be easily detected and leakage does not affect the operation parameters of the process. Then you can have normal joints where the efficiency has to be rechecked and reconfirmed. Coming to the safety factors. So here the safety factors mean the ratio of material stress to the working stress. Okay. So it is what are the stresses which is expected to experience during the operation. So that is a safety factor. So it is again a standard value. For a process vessel, 3 to 4 is added, and for storage vessel, it is 2 to 3 is added as a safety factor. And there are numerous design code which has been available. So that design code also has to be checked before, or all the standard or the material or these material of construction and joint efficiency has to be referred based on the applicable design codes. The components of the pressure vessel includes shell, heads, nozzles, flanges, supports, and manholes. So shell is the main part of the pressure vessel. It can be cylindrical or spherical. And here we have all the attachments goes to the shell to make it as a complete process vessel. Heads, there are different type of heads which we discuss in the next slide. Nozzles. Nozzles is a cylindrical projection attached to the vessel or a pipe to provide an inlet, outlet, and connection. So some of the nozzles are inlet nozzle, outlet nozzle, vent nozzle, drain nozzle, and manway nozzles. So the fluid passes through the nozzles and it is sometimes directly welded to the head or shell of the pressure vessels, or nozzles can be connected by using flanges. Okay. So flanges is a rim, a projecting rim or a collar used to connect a pipe to an equipment by bolting together. So here when you have a flanges, you can connect a pipe using bolts, nuts, and the gasket. So when we are connecting a pipe or any attachment or any hole which is there in the pressure vessel by using a flanges, we can ensure leak-proof mechanical joint between the components. Some of the flanges are weld neck flange, slip-on flange, blind flange, lap joint flange, and socket weld flange. It is easy for removal and maintenance and also for inspection purpose. Supports are these head and the shell will rest on the ground or land by using support. There are two types of support. One is vertical support and horizontal support. And horizontal support is called saddle and vertical support is called bracket or leg or rim support. Manholes. Manholes are the provisions which is present in the shell for inspection and also for cleaning purposes. Next, coming to detail on coming to the type of enclosures. The heads or enclosures are classified as flat head, hemispherical head, ellipsoidal head, toruspherical, and conical head. So coming to the diagrammatic representation, We can see D as the thickness of the head, SF is straight flange, D naught is diameter of the flathead. Similarly, Ri is inner radius and T is thickness in a hemispherical head. SF is straight flange, H naught is the height which is added in the hemispherical head, and RKA is the knuckle radius. Similarly, torus spherical head, and also we have conical head with the alpha apex angle as right. So coming to flatheads are generally used for manholes in low pressure vessels to bind any flanged opening. Okay. So they are used for closures for smaller diameter vessels at low pressures. It is the simplest of the head to construct, but it is the thickest. So the cost of the fabrication, material cost is high and fabrication cost is low. Coming to the elliptical head are formed on dies in which of has a diameter cross section of an ellipse. So you have ratio of major to minor axis as 2:1. So what is the advantage? It has good strength to cost ratio, easy fabrication than hemispherical heads. It is used in chemical reactors, pressure vessels and process columns. Coming to hemispherical head for a given thickness, it is the strongest among the head. So this head is used to resist the pressure twice as compared to an ellipsoidal or a cylindrical dished head. But it is the most expensive because it can withstand the high duty operation, and we have used the material wisely or efficiently. The material has been used to design this hemispherical head. Next, coming to torus spherical head. Torus spherical head is also known as torus spherical dished end or torus spherical ends. It is used for pressure tanks to store liquids and gases. It consists of a spherical surface and a cylindrical edge of a certain height. So here, the material can be carbon steel, stainless steel or any ferric metals that can be cold worked. The stress distribution is not as uniform as elliptical head, but the manufacturing process is easier than elliptical head. So that's what elliptical is a better option than compared to elliptical head for the processing operations. Next, coming to conical head. So conical heads are used as a bottom for a variety of equipments. Preferably, it is used for discharge and loading. So examples are evaporators, spray dryers, crystallizers, settling tanks and silos. So it helps in accumulation and removal of solids. It has easy connection between different diameters. So it is used as hoppers in cyclone separators and also in storage silos. Next, coming to the design of a conical head. We will see an illustrative problem on the conical head design. Coming to the formulas for the design of the conical head, it includes the thickness of the head at the junction of head and the shell and also the thickness away from the junction. To familiarize with the terms, T refers to the thickness and P refers to the internal pressure, DE refers to the equivalent diameter, Z refers to the factor of discontinuous stresses, F refers to the allowable stress or the design stress, and J refers to the weld joint efficiency. Thickness away from the junction, we have a formula where P dk by 2fj minus P into 1 minus cos alpha, where alpha refers to the angle of inclination or it is also known as half apex angle. To account for the z factor, we need to know z values, alpha values, where alpha is a half apex angle and it varies from 20 degrees to 60 degrees. The normal standard value for a conical head is 30 degrees, and if it is greater than 30 degrees and within 60 degrees, the cones are said to be steeper. So this alpha is decided based on the transition which is required in the pressure vessels. The Z value is accounted in the problem and it measures the 1.35 for 30 degrees. So as we can see, the stresses which is involved in the conical head We need to calculate the thickness at the junction of where the head and the shell meets, and also at a certain distance away from the junction. Let us understand the example of a conical head by this problem. This problem discusses on a process vessel is to be designed for a maximum operating pressure of 500 kilonewton per meter squared, which is the P value. The vessel has a nominal diameter of 1.2, which is D, and it has tangent to tangent length of 2.4 meter. The vessel is made up of IS 2002 to 1962 grade B quality steel having allowable design stress value of 118 meganewton per meter squared, which is defined as F at a working temperature. The corrosion allowance is suggested as 2 mm for the lifespan of the expected for the vessel. The vessel is said to be fabricated according to class 2 of Indian standard specification, which stipulate the weld joint efficiency of 0.85. If the process vessel is to be provided with a conical head of half apex angle 30°, determine the thickness of the head at the junction of head and shell and also the thickness away from the junction. Let us just solve the problem for A and B subcategory. To calculate the thickness of the head at the junction of head and the shell, we have seen the thickness is calculated by using formula PDZ by 2FJ. Since the angle of inclination is 30 degrees, Z value can be accounted as 1.35 and J is weld joint efficiency which is 0.85 and F is allowable stress which is 118 meganewton per meter squared. DE is equivalent diameter of 1.2 meter and internal pressure of 525 kilonewton or 0.525 meganewton. Substituting these values, the thickness of the conical vessel at the vessel at the junction of head and the shell is given by 4.2 mm. The thickness can be round off to 5 mm and the corrosion allowance of 2 mm can be added so that the thickness becomes 7 mm. Now we have to calculate the thickness away from the junction. As we know from the formula, T is equal to PdK by 2fj minus alpha into cos alpha, where dk is the maximum inside diameter of the cone at the distance of half det by cos alpha to the power of 1 by 2 from the junction. So it says dk is a diameter at certain distance from the junction. The distance is given by the formula of half square root of det by cos alpha. Since we already know the values, the T is a thickness calculated from the previous step and DE is equivalent diameter, and alpha with alpha 30 the cos alpha is 0.86 and the distance accounted as 50 mm. To find out the diameter dk at a certain distance away from the junction, let us understand from this diagram. The dotted circle here in the cone refers to the portion from which we have to measure the diameter. So we want the diameter of this dotted lines where we know the total diameter of the vessel. The total diameter of the vessel is D0, which is 1200 mm, from which the internal diameter can be found out by subtracting the thickness on both the sides. So if the thickness on one side is 6 mm, if we subtract the thickness from both the ends, we get 1188 mm. That is the internal diameter of the vessel. Now we want to subtract x distance on both the sides so that we account only for dk. So dk is di minus 2x. And how do we calculate this x? See, when we know the calculation at a certain distance away from the junction, which is 50 mm, then we form a right angle triangle with the angle as 30 degrees. The opposite side is x and the hypotenuse is 50 mm. If we can calculate sine 30 from by which is equal to x by 50, x can be taken as 25 mm. If x is 25 mm, on a single side, on both sides it is 50 mm. So we need to subtract the 50 mm from internal diameter of the vessel. dk is obtained from di minus 2x, which accounts for 1138 mm. So dk is the diameter of the cone at a certain distance away from the junction. So here the illustration of calculating decay is given. We are now using this decay to find the thickness. As we already know, the thickness of the conical head at a certain distance away from the junction is given by this formula. Here dk is a value which we have found out. On substituting dk and alpha is 30 degrees, we can find the thickness as 3.44 mm. Previously, if we can remember, the thickness at the junction of head and the cell is 4.24 mm or 5 mm. Here, this thickness is 3.445, which is round off to 4 mm. So now, understanding from the conclusion, the difference in the thickness is only 1 mm in the two regions. So there is no justification in using different thickness of the sheets at the two sections. So as we understand, the whole thickness is 7 mm, and now the thickness at the away from the junction is 5 mm. So the difference is only 2 mm, and hence it is suggested that the shell or the conical head can be designed with the greater thickness or a single thickness of the sheet. It will be recommended, or it will be more economical from the fabrication point of view to use single thickness, and the larger of the one is chosen. So the conical head of 4.25 mm with corrosion allowance of 2 mm summed up to 7 mm thickness can be used for the fabrication of conical head. So this brings the references of this problem is from Bhattacharya Besi, Introduction to Chemical Engineering Equipment Design, and also Joshi, Process Equipment Design, 4th edition. Thank you.